Okay, cool. So today we'll basically look at CNN, like the entirety of CNN, and then we'll go through the AWS. So convolution neural networks, these are not all that different from the artificial neural networks, except we have more different types of layers, and the function this performs is pretty useful. And we also have a bit of heuristics behind why we do certain things. So that's pretty much going to be this section of the summer school. So a convolution neural network. Okay, we'll first look at what convolution is. So look at these two images. Let's say you could. I'm telling you, you could take this image in the left, and you could extract only the straight edges. You could also extract only the horizontal edges, or you could just extract the corners, like the bottom left corners or bottom right corners or top right corners, like these. This one, this one, this one. So these kind of operation, these kind of extracting features from an image, we do this by convolution. So what exactly is convolution? For that, we'll first look at how exactly we process images. So what happens is when we give an image and tell Python to read that image, what Python does is it'll take all the pixels in the image and arrange the pixel brightnesses in a matrix. So this is how a black and white image will look like. So look at the left top pixel that will correspond to the left top element in this matrix. So the brightness there is 0. Similarly, if you look at this element, the brightness that corresponds to it is 0.4, and this is 1, etc. So this is how black and white images are processed. Similarly, you could do the same for a color image. So let's say your file format is JPG. Then you'll have 3 such matrices. So your array shape will be XY3, not 3YX, 3XY. It'll be XY3. We'll come back to that later. But what we have pretty much is the pixel brightnesses of each pixel in the 3 colors. Similarly, if you have a PNG file, then you're going to have 4 such things, which will be red, green, blue, and opacity. So this is how images are vectorized. And what we do to these vectorized images, these matrices, is we apply filters on them. And this is where the name convolution comes. Convolution is pretty much this operation that I'm going to talk about. What happens is you take a filter, you place it on your larger matrix. You slide it along your larger matrix. What I mean by sliding is, for example, take these 2 matrices at the center of the screen. So first I will place this -1 on this 1, and next I'll place this -1 on this 2, so that first it will cover the top 2x2, and then it will cover the right 2x2, top right 2x2, and then I'll place this -1 on this 2, so it will cover the bottom left 2x2. Similarly, I'll place this -1 on this 2, so it will cover the bottom right 2x2. Similarly, you can do this to a larger matrix as well. So pretty much what we're doing is we are taking this smaller square and sliding it along the larger one, so that we will cover all possible positions in which the smaller square is not going out of the larger one. And at each of these placing, at each of these positions, what we do is we scale this smaller one by the element that we are placing it on, and we will basically take a superposition of everything that we're getting. For example, like take the same example. I've shown what exactly is happening here below. So we're placing this -1 on this 1, and we're scaling this 2x2 by that 1. So we have -1, 1, -1, 1, and then the rest of it is 0. We add that with placing this filter on 2, scaling that with 2. So we have -2, 2, -2, 2. Like that, we're placing it on this bottom 2 after that. And then we're getting -2, -2, 2, 2, like that. So we take a sum of this. So so this is pretty much convolution. But notice one thing, to this inner part of the matrix, that is, for example, this element, this will get contributions from all 4 sides. But the okay, wait, before going to that, let me know if convolution was clear. Like if you have any doubt in what I just told you, you can ask right now. So I'm assuming we have no doubts. I'll just quickly go through it once again. So what we do is, to process images, first we will arrange it in a matrix. Python will do it for us. And after that, what we do is we apply a filter on it, and we convolute a filter on it. And this convolution operation is when you slide the filter through the entire matrix. So we'll start from this 1. So first we'll start here and then we'll end here. So we'll go through all of that. And then we'll, at each position we're placing it, we'll scale this filter with wherever we're placing it. And then we'll add all of them. We'll basically superpose all of them, like I've shown below here. So in the end, we will get a larger matrix. And so that's what I'm going to talk about right now. It shouldn't be of this size, because let's say we take an inner element, say we're taking this one that I'm highlighting right now. So what is happening here is it is getting contribution from 4 sides. It's getting contribution from this one, as I've shown in this first matrix, and it's getting a contribution from this 2, as I've shown in this second matrix. And it's also getting contributions from this 2 and this 2 that I've not shown. But so all the inner elements are getting contributions from all sides. But the outer elements, so this -1 here, that's not getting contribution from any other position except this one position. So to avoid that, to avoid these outer positions, I mean these outer elements causing a discrepancy, we just throw them away. We don't use them. We'll just use the inner part. But all of these details we don't actually need to care about, because the computer will take care of this. But I'm just telling you so that you know that it's happening. So whatever we did so far, that is fine. We can think about it as superposition, and it's a good way to think about it. But then for a computer to process it, it's going to be a very big operation to place it at each position and then to superpose it by adding those big matrices. It's not going to be that efficient. So we have a much more simpler way to do this. So what we do is we will take the transpose of this matrix, and then we'll sweep this transpose throughout our image. And then at each position, we will add the product of, okay, let me just show you. So look at this image. So our filter was -1, 1, -1, 1, which we just took the transpose of. So it's 1, -1, 1, -1. And then we swept through this through the entire image. So at first it was covering the first 2x2. Now it's, and then it covered the second 2x2 like that. So we are at the last position right now. So what I mean by taking the sum of products of the terms that are at the same positions, what I mean is, so look at this picture, we have 2 and 1 at the same place. So we'll take the product of these two. Like that, we'll take the product of all 4 of these groups, all 4 of these duplets, and then we'll add them. This is a much simpler way of doing convolution. And these are the same things. And I will not go through the proof of this, why these are same things, because it's going to take a lot of time and mathematical figure. But I'll tell you one thing, you can try proving this by proving the single like 1D version first. What I mean by that is, say you have f of x, and whenever f of x is 1, or whenever f of x is some value, you're having another okay, let me just show you what I mean. So let's say our f of x is 0 everywhere. Y equals 0 everywhere. Y equals 0 everywhere, except 0, 1 and 1, 2. I can't graph piecewise here, so I'm putting 2 different points here. So to get an idea of why that works, what I'm gonna ask you to prove is, what I'm gonna ask you to do is, let's say you have another function g of x, which gets superposed onto these f of x positions. So like, say g of x is this equals this triangle here. So say at every such, like whenever your first function is some non-zero value, this g of x gets superimposed at that position. So so for this f of x that I've given you, this will become I will disable this, and then so your output will become g of x plus 2g of x minus 1. So what exactly is happening here? We are adding g of x at x equals 1, and we're adding a scaled version of g of x at x equals g of x at x equals 0 and a scale version at x equals 1. So I want you to think about how you can mathematically prove it, and you can take summation instead of integrals, like deal with discrete versions or whatever. So if you do that, you can prove this. That's how you prove it. I'm not going to go into it, and you don't actually need to understand it to implement CNNs actually. So let's just leave it there. So this is what the computer will do, and the layer in your neural network that does this is called a convolution layer. That's quite obvious. And here is where I come back to the shape of your image matrix, image array. So our image array will be of shape, it's height, comma, its width, comma 3 for RGB. Or it's not going to be 3, comma height, comma width. That's just how Python processes it, and that's just how that is the same way how TensorFlow will process it. So we will stick to this shape, and so that's like having a matrix of like a matrix that has elements which are arrays, and those arrays are of shape 3 or 4 if you are dealing with a PNG file. But yeah, so the input shape in your first convolution layer, and why I'm telling you this is because you will have to give the input shape in the first layer, in your first hidden layer, which will be a convolution layer, and there you'll have to give the input shape height comma width comma 3 or 4 or 1. And in your convolution layer, you will also tell the layer the filter size. So typical filter size is 3,3. So we'll throughout this project we'll be sticking to 3,3. But yeah, you will have to give it a filter size, which will be the size of your filter basically. And how exactly a convolution layer works is uh, it'll initiate filters, it'll declare filters with random coefficients, I mean random entries at first. So like if your filter is 2,2, then it'll probably have 4 trash values in the filter, and then it'll start optimizing, it'll start changing the value of the filter as we learn, as the machine learns. So that is how a convolution layer works. You can also put on an activation function to your convolution layer, and the input output weights, the weights of the arrows, they just stay the same. It's just that this layer is doing an additional transformation to your input along with an activation function too, and that's about this layer. And we have more layers in a CNN. Okay, wait. Okay, tell me if you guys understood what I mean by convolution first, and then understood how exactly a convolution layer works. I mean, speak up if you have any doubt in these. Okay, so I'm assuming we have no doubts, but I'll keep recapping everything I tell in this session because this is the final session and this is going to be everything about CNN, and it'll be better if we don't have any doubts. So we started off with this example. Imagine if we could do this, and this is exactly what convolution does. So before going into that, we will first think about how exactly we are going to process images. We are going to arrange this image in a matrix of subarrays, and those subarrays will be of shape 3 if it is RGB, 4 if it is a PNG file, or 1 if it is in grayscale. And what happens in convolution is a filter is getting superimposed, multiplied by these image. I mean, a filter is kept at each position in the image and is scaled, and then it's getting added. So that is superposition or convolution. And there's a more efficient way to do this, which is you take the transpose of the filter and you sweep it through the image, and then you add and then you do this kind of an operation. You everything that is there close by, you take the product and then add. So that's how you get your convoluted image. And what exactly a convolution layer does, it will initiate a filter like this of the given size with trash values, and then it will learn those values. And everything else about the layer stays the same. The input gets added and the weights are there in the arrows that will get optimized. Everything else is the same. And for the input shape in your first convolution layer, it is going to be height comma width comma 3 and not 3 comma height comma width. And so yeah, it will function like you have 3 input layers. I mean 3 input neurons basically. Like this last 3 will make the layer function as if you have 3 input neurons. So if it was 4, it will make it'll make it function as if it has 4 input neurons. And so we're done with understanding what exactly is convolution, and we're done with understanding what exactly a convolution layer does. So now we'll move on to more layers that we will be using in a CNN. firstly, we will be using a pooling layer. So what a pooling layer does is it essentially reduces the size of your image. And there are two ways to do it. I mean, there are many ways to do it, but the common two ways is max pooling and average pooling. Max pooling will just take the maximum element in your group. A group or a pool is dividing the entire image into small groups of the given size. So like if I give it the size 2,2, then 9, 4, 2, 1, these four will be one group. 2, 1, 5, 4, these four will be one group, like that. And the common two types of pooling is max pooling and average pooling. Max pooling is whatever I've shown here. It will take the maximum element in a pool and just put it in a matrix. And average pooling is just taking the mean of every element inside and putting it in the matrix. So that is pooling layer. You'll have to give it a pooling size, and everything else about the layer functions just like dense layers. Like the inputs are going to have weights, the outputs are going to have weights, and those will get learnt, and everything is the same. And there's a flatten layer. What we will be doing is we will process the image throughout, and then we'll flatten it. Flatten is same as the flatten in NumPy. What happens is it'll just take these, say we are putting a flatten after this pooling layer in this example. So it'll just take this image and then it'll make it 4 neurons with the output 9, 5, 3, and 7. That is basically flattening it. And dropout layer, this is added after after dense layers that will come after flatten, so that you avoid overfitting. So like, let's say you put on a dense layer of 500 neurons, and then you can put a dropout layer to make sure it doesn't overfit your training data set. Dropout will pretty much just disable some dense layers depending on whichever is the best to disable. So in the end, so this is like the most basic design for a convolution network. So we have three input neurons. So the input shape here is 128, 128, 3. And then we have a convolution layer with 10 neurons. And the convolution layer, like we discussed before, will chuck out all the corner elements to keep only the centers, because only centers will have contributions from all possible positions around it, like so that there's no discrepancy in the corners. So like the corners alone don't become dark because they don't have contributions from the other sides. So this is reduced in size because of that, if you see. And then there's a pooling layer which is taking groups in this convoluted layer and making it smaller. And then we have a flatten layer, which is just flattening everything into 2250 neurons. And then we have a dense layer. And then there's a dropout layer to disable some neurons so that it doesn't overfit. And then there's a dense layer, which is the output layer. So this is the input layer, this is the output layer, these are the hidden layers. So this is pretty much what a CNN would look like. If you have any doubts right now, you can speak about it. I'm assuming we don't have any doubts. So we saw how exactly we process images. We saw the shape of an image that we process in Python. It's not going to be 3 at first, it's going to be 3 at last. And then we saw how exactly convolution is done, and we saw how more efficiently you can do it. And then we saw how we chuck out the corner elements, the outermost elements, because they don't get contribution from all possible positions. And then how exactly a convolution layer works, it will initiate filters with random values, trash values, and then it'll optimize. And then other layers, pooling layer will reduce the size by either taking the max of each group or the average of each group. And notice here that when we swept the filter through the image, we put it on all possible positions. But when we make groups in the image, we will make sure that like we don't put it in all possible positions, like the groups, but we don't let the elements overlap, if you get what I mean. So like if we are sweeping the filter through this matrix, we will first sweep from, I mean, we'll first put it on 9421 and then 4215 like that. But then when we are making groups, we will put 9421 in a group, 2154 in a group. We won't make a group of 4215 because we don't let uh, an element be a part of two groups. But we do that when we are sweeping the filter through the matrix. So that is something to note here. And then so yeah, so the final CNN is going to look something like this. So now that we know what exactly is going behind a CNN and how a final CNN is going to look like, we'll start implementing it. So everything in implementation stays the same except for the things that I'm going to show here. Firstly, we are going to vectorize the image. So we are going to get an array of shape, height, width, 3. So for that, what we do is we use matplot libraries imread, image read. So we use this line. So what this will just give you whatever we need. We need height, width, 3. This will give you exactly that. And if you want to process it in grayscale, you can use this. So that's how you vectorize image. And sometimes you might want to visualize what an image looks like. I mean, after processing or something. So for that, we use this im.show. It'll pop up a pie plot in which your image is shown. Or you can do that in grayscale also. So that is visualizing image. And then these are the layer objects. We have the convolution layer. The syntax is this. This is the number of neurons. This is the filter size. This is the input shape. Like I told you, there's 128, 128, 3, not 3, 128, 1. And this activation function, this is optional. And input shape, like in artificial neural networks, is given only to the first convolution layer. And then we have a flatten layer and then dropout. This 0.2 signifies that 20% of the previous layer is dropped out. And then we have a max pulling layer here and pull size. So these are the three things that you'll need for a basic CNN. And here is one more thing with implementing a CNN. And this is more like a technique rather than basic implementation. So I'll tell you guys more about the technique later, but I'll first tell you why we use this technique. So firstly, when you have a very small data set, your just learning from whatever you have might only get you something like 60% testing of it. So what we do here is, let's say you take the image and you flip it and then you feed it again. So for us, these two look the same. Like there are two cats and it's the same cats, and we can say that this has been flipped, but the computer won't know the difference. I mean, the computer won't know that these two are the same image. For the computer, these two are completely different. Like a similar effect can be achieved by zooming into the image or moving the image a bit or shearing the image a bit. Shearing is like skewing the image a bit. Or you can also resize the image or whatever what happens is the same image data is being used, but it's fed into the neural network in a slightly different way, so that it almost is like you have a larger data set. It's extracting the most out of each image. That's pretty much what this image data generator is doing. And there's also another issue this will solve: overfitting. Say you feed the same image to the model like 150 times. in 150 epochs. So this will definitely overfit your image, and that will be a problem. Instead, if you feed slightly different images, then it's not going to overfit the same image. And also memory. Let's say you have 2 GB of data, and then you're trying to load everything into one numpy array. That is definitely going to get your GPU very angry, and your GPU is probably not going to take it. So instead, what you can do is you can use this attribute of an image data generator. We'll come back to the exact code later. And what this attribute will do is it will take the image real time from wherever it's stored, instead of putting everything into a numpy array at first and then processing it. At every batch, it will take images and feed it into this into the model. So yeah, these are the 3 reasons why we do image data generator. And how exactly we do it is we first arrange our training directory in this form. So within the training directory, we put all the images into their classes. So let's say we're doing classification task. Our AWS is pretty much a classification task. So we put the images in their classes. So for example, this is what the training directory of the AWS looks like. Let me show you. So this is the training directory. So I have put everything in 6 folders. And if you go into each folder, there are images. So this is how you format your training directory. And then you run this following code. So this will first initiate a generator object. And then this will initiate an object for taking images directly from directory instead of loading it into a numpy array. And then this is just your usual fit function. You don't need to use fit underscore generator. In the newest version of TensorFlow, the usual fit of also takes the same arguments and does the same job as fit underscore generator. So like you can remove this generator in this function, or you can also use it. It doesn't make a difference. So yeah, this is how you implement a generator. So that is how a CNN is implemented. I will quickly recap this again because this is pretty much the most important thing in this software module. So we started off. Okay, wait. Let me not go there. That we recapped it too many times. So, okay, a convolution layer. It'll initiate a filter with trash values, and then it'll learn from the dataset. And this filter is going to be swept across every position, and it's going to perform convolution, which is pretty much superposition, but in a more efficient way. And your input shape to your convolution layers is going to be height, width, 3, not 3, height, width. And there are other layers in a CNN. There's a pooling layer which will create groups, and the groups don't have overlaps. And these groups, say we're doing max pooling, then the maximum element is going to go into the output matrix. And we have a flatten layer which will just flatten out everything. We have a dropout layer which will disable neurons so that there's no overfit. And so this is what our CNN will look like in the end. And then for implementing CNN, first we vectorize the image, and then we can visualize it whenever we want. And these are the layer objects. I mean, these are how you declare layers in your CNN. And everything else about declaration, I mean, everything else about implementation is the same as our usual neural networks. And then we have image data generators. These are used to solve 3 problems. One, having a small data set. Like, for example, our AWS model had only 2000 images to learn from. And we were able to get only 60% accuracy with an usual CNN. I mean, by usual, I mean not using data generator, just feeding the images as they are. So that is a small data set. So what we did is we used this image data generator, which just changes the images very slightly. It might rotate it, it might zoom in, it might move the image a bit, it might pan, it might skew the image a bit, or whatever. To us it's the same image, but to the computer is completely different. This also solves overfitting. The same image is not being fed in, and this also solves a problem with memory. So you can still keep using your GPU instead of switching back to CPU in TensorFlow, like GPU accelerate. So, and how exactly we do it? We format the training data. I mean, yeah, the training directory in this format. We have classes, and then if we go into class, we have images, and then this is the final code to implement it. And we don't need this generator. I'll remove it from the PDF. So yeah, that is pretty much CNN theory. And if you have any doubts, you can ask right now. If not, then AM will take over with showing you guys the AWS.
I will give it 2 minutes break or something, then I will start up with AWS.
Yep.
Okay, so I'll start now. Is my screen visible?
Wait, should we show them what convolution looks like, as in, say, edge detection or something, like an example?
If you have anything to show, like, you can show.
Wait, I'll show them next. After that, you go on to it.
Yes. Okay then.
Just a second, I'm digging up the link I used here. Oh, okay, cool. So, okay. So I am going to upload one of the images from the training set. And I'll just run a simple filter on it. So there's some idea of how exactly conversation. So I hope the image is visible. So, okay, wait. Let me go to huh. So I uploaded a color image, but this thing supports only grayscale. So yeah. So this is what the image looks like. And
Yeah, you're not sharing.
oh, I'm not. Oh, okay. Cool. Just is it visible now? Okay, cool. So look at this image that I've uploaded into this this thing. So this is our filter, and I have put one at the center and nothing around so that there's no change in the image. So what I'm gonna do now is I'm going to detect only the outlines in this image. So this is an example filter. We don't expect you to know uh, the values and stuff. So I'm just going to enter it because I played around with it before. So what this filter I have entered here does is it will detect only the outlines from this image. I mean, it's definitely not perfect, but if you look at it, it has traced out only this bottle. So this is how convolution works practically. So what is happening here is it is flipping this. I mean, it is transposing this filter, which is going to give the same filter, and then it's sliding it around, and it's doing this multiplication. I mean, addition sum of products that I showed here. Here, this is doing that, and it's getting this image as the output. And similarly, in okay, give me a second. I'll do the 4 example if I have the 4 that I showed at first. Okay, I think I don't have the 4. Or is this the 4? No, okay. Oh. So yeah, I'll do an edge detection on another image. So this is one of the images in the metal data set. I mean, the metal class. So yeah, and in this I am going to detect edges. Yeah, this is going to detect only vertical edges. This is the filter that we ran on that 4 in the first page to get only vertical lines like this. So yeah, that I hope that gives some kind of intuition into how exactly convolution is helpful for us. Now AM will move on to show you guys how exactly a CNN is implemented.
Yeah, okay, I'll start. Is my screen visible?
Yeah, it is.
So now we'll, whatever I start in the slides, now we'll implement in the collaborator notebook. And to do that, as we explained in the previous session, we'll import all the library. First one is NumPy, which we explained in the first session, is step NumPy and pandas. CB2 is one of the libraries which is used for like image viewing and like all the image related operation. But we just imported and not using it here. Like you can either use CB2 or matplotlib.info or Imread. Either of them works. And you see, we imported TensorFlow, uh, and from the Keras API, I explained this term like Keras.callbacks. Last session I did this, and I also sent a link if you have gone through this, the model about model checkpoint and LD stopping, and like also all the layers like convolution, flattening, max fooling, dense dropout, these layers, and all sequential layers. And as reflected in the slide, we imported image data generator, and this OS Globe and random. OS and Globe are basically it's for file operations in Python, like connecting directories, extracting files from directories. This, and random is for generating random numbers, and matplotlib is the plotting thing, and gif-file.jw is for unzipping gif file. We don't need this in Google Colab. Like if you're uploading a file, you need this. Like just as you can see the code, like if you're doing in a locally Jupyter notebook, you have to like, and your data set is in a GIF file. So you have to just like first open the file with this command jdf.gif file. Okay, I'll show you one. Let me open data set. This data set are using. First, I'll upload the. I'll upload. I'll explain after it get uploaded. So what basically I did here, I mounted my Colab notebook to Drive, Google Drive, so that I can access all the contents in my Google Drive using this. And from this command, you can mount your Colab notebook to your Google Drive and access all the contents in the Google Drive. And I have my data set. This is the data set using. I'll go through the data set once to review. Since it's a zip file, okay. I'll go through the data set. Give me 1 minute. Where is the zip size? Can you see my screen?
Yes.
Yes. So like these are the data. I'll even the grade. You can view different images of this data set. Like these all consist the cardboard section of the data set. Like we have multiple images and we are training this data set to the model. I'll post the dataset link in the chat so that you can. This this is the plastic dataset. We have plastic, different plastic, and I'll go through metal. It's metal. This is metal. So we have this training data of 2000 images which are aging, and this this file. This file has different results which we'll use for the prediction of our data. So we'll validate like how much our data is. Basically, we'll predict these images using our after training our model. We'll predict these images using the model, like how well they predict. And from the training dataset, we'll split some percentage to the validation dataset and find accuracy of the model using that. So I'll run through the dataset. We can get the dataset here, I think. This will share the dataset to them to try out. And Rishi, can you hear me?
Yeah,
Hello.
I can hear.
Should you share the dataset with them?
Okay, cool.
I'll put
What
this.
about we just share it after the session?
Okay, then fine. Yeah.
Yeah. Okay.
Here, what I mounted the drive, then this dataset, this zip file, dataset submersible chain and zip. I unzipped the file using this command. So this file got stored in like all the extract got extracted in drive. I'll show you how it's like it's there in the this is there in the drive. Just I just unzip this file so that like I can like we can access all the files inside the dataset in the Google Color. You can see what's in the dataset here. This period B. This is training data. This is prediction data. The training data has 6 categories. You can see cardboard has this many images and all the things you can see. So by unzipping we get like we don't need to upload the file now. Like we can just do by connecting the drive and unzipping the dataset. Now we after for our training path, so we make a named the path as like assigned the variable date path, and this what when we run like use this date path variable, it just gives the directory of the training dataset. And what this command does, ki like I saw globe and OS I explain like so I think we won't have time to explain more about globe and OS.
Yeah,
We'll
I'll
send
leave that.
after the session. Like I'll tell what it does basically. So inside the training dataset, wherever the whatever the .jpg file are there, it just connects all of them and appends them into one file, like one list. Basically, it makes a list of images, like path of images. Like the list has, I'll print it and print the image list for it. See, basically, it makes a list, makes an array of. Remember. Yeah,
You
the
can
list
do
of
the same. You can do the same manually with OS modules list directory.
yeah.
It's not that important for the model. You can
Yeah, just so before doing, I'll print the length of this list to see how many images do we have for training. That we have 2091 images for training the data set. And now as image data generator, it like it skews and it does all the kind of transformation and all inside the images and like generates multiple images from a single image to increase the dataset size so that I can get a better training accuracy and our model works as explained in the slide. Like, we can flip the image horizontally, vertically, then rescale. What does this rescale does is this I'll explain. So the RGB section of the image is basically integer from 0 to 255. So when we train the model, it takes to value like all the till 255. So since it's a too long range of values, so it takes longer to train the model. Like we need more time. So when we rescale from 0 to 1, the model works faster and trains in less time. And these are all augmentations to generate multiple images to increase our data set. And And using this problem directory command, like we set the target size, our image size is 300 plus 300, and for training we set our batch size as 32. And so this, since we first will do both, like from training the folder will split one some 90% for training and 10% for validation. Here validation split 0.1. It's just like the SQL and Sanskrit-learn trend test, right? Like here what we do is splitting the 0.1 fraction of the data set for the validation, and rest of the fraction is for training. So using this argument subset equal training, this trend generator goes for training, and like test generator goes for testing the data set. And using this we made a dictionary connecting all the labels and the belonging class name. Like cardboard as 0 and glass 1, metal 2, paper as 3, like this. And this will show what the image generator does. This will print all the images of what trend generator has. You can see like this is 18, but like flip the this image. It flipped the image and took some different, like made a different image out of the data set to increase the data size for more training accuracy. I'll rerun. I can see this is also flipped, and showing all. This is also a bit skewed, and this also like this. That image generator does to increase the data set. Now we'll print the image shape and the batch shape. Here we get that our image shape is 300 plus 300 and 3 layers cause of RGB and 32. So from this we get that our input say layer to convolution would be 32. Since this is the image, like initial image layer. And here we are writing all the labels and dictionary as a text file. I am just keeping it as a reference. You don't need this. Till now, anyone has any doubt regarding image generator or starting also? And if you are using a local notebook or just uploading file to Google Colab and want to extract a zip file, you can use this command. What this does? This opens a zip file. Then the second line does it extract all the files inside the zip. And now you have all the file, like whatever is inside the zip, you have extracted in the Google Colab, and it will show here. After that, you close the file and you can access all the whatever was inside the zip during running also. Anyone got any doubt? I'll wait for one few minutes. Then 1 minute, then start building the model. Okay. This is very important. First, I mentioned in the last class that saving a model and using it for later. Here you can see as I saved a model, trend model.h5. Okay, I can explain you about HDF5 model. Okay, I'll just search it. HDF5 TensorFlow to show you what HDF5 does. Where is the one? Give me a minute first. Yeah. Okay, and this is basically a KRS format. Like what we do is like it saves the model in HDF5 format. Can you see the screen like TensorFlow.org? Hello, can you see the screen?
Yeah.
Yeah. So when we train the model, after training the model, we don't want to lose whatever weights and features we got from the training. So what we do, we just this form using this file format of KRS, we save model as .s5. Like here, as you can see, I saved this model as train model .h5. So when I run the training, in each epoch, it saves the whatever weights it get. If it's increase, like we can put the conditions here, but uh, in each epoch, if it satisfies whatever conditions, what this does is this checkpoint, this takes that weight of that epoch and stores into the H5 format, and I can later use the model to the saved model to predict the data.
This is particularly important when you're doing like training separately and
Yeah,
prediction separately, and that is how we usually do it, because you just train it once and then you deploy the predictions.
yeah, exactly. Just you don't need to train every time. Just train it once and save it and use it later. You can just use model.save also, but it's model.checkpoint as really stopping has a lot of features, like a lot of conditions, like it can give you a better weights than model.save. So here what it is, sir. We declared a checkpoint, which is model checkpoint using the syntax of this as I explained later session. The file for it saves the weights at this file. Then it monitors validation accuracy. This model checkpoint. So it will keep an eye on validation accuracy, and when like it will print, I'll show you it. It will print the validation accuracy improved from this to this. Validation accuracy did not improve. So it will keep an eye on me, and on each epoch it will print. And Barbos as one, it will print both training and validation accuracy during training. That I explained previous session. What this command does is whenever validation accuracy increases on each iteration, it saves the model to the file, and all the callbacks we had. You can include more callbacks also, like how many callbacks? One early stopping also, whatever callbacks you want. There are mainly two kind of callback: early stopping and model checkpoint. We're using just model checkpoint here. You can also use early stopping. What it does is whenever your validation accuracy decreases from the first previous one, it stops the training and goes saves the model. And now I'll go to the whatever model you used. So since the image size here is 32, our first convolution layer will be 32, and input size is image size is, as we designed the train generator, is 300 plus 300, and 3 is for RGB. And we're designing the convolution filter as 3 plus 3, and our activation function is ReLU. ReLU is basically f of what f of x max of 0 and x. There is ReLU. Uh, so this is our architecture of the model. First we did one convolution model of input model, basically you can say, which takes the input and convolutes. After that we added one more convolution model of 32 channels and same 3 and 3 filter size with activation as ReLU. And then we added a max pooling layer of size 2. So this is our first block of layers. In the second block, what we did is we added again two convolution layers of size 128, and filter size 3 as activation same as ReLU. and also one pooling layer of size 2. And in the third block we used two convolution layer of 32 and one pooling layer of 2. So you might think like, how do you know like how many layers to use and what to use? So I think like begin with low layers. If it's underfitting, increase uh, till it's not overfitting. Like, and if it's overfitting, you are like, you start with basic level of layers, and you can see the validation accuracy is it saturates early, then increase the level and like what this number of channels and number of layers, and it might overfit also. So just add the dropout, and if it's overfits, or else you can use preloaded layers. There are many like popular models available like RaceNet, LXNet. Like you can go up on that and use that. But like if you want to make your own layer, own model, then start up with two convolution, two dense like that. Then yeah, when you see that it's saturating early, just increase of the layer size and channels. And after that, if it's overfitting, like the overfitting and underfitting case, we explain last class mostly. So like you have many ways to solve that. Like more like this is one of the way to store like model checkpoint is one of the way to manage overfitting. Another is weight regulation, uh, and the third one is dropout. So here I have added some dropout because I like when I built the model, like started building the model, I started with less layers only. Then it like kind of saturated at 50 or 55, something like that. And I used image generator, and it got improved to somewhat 65 something. And then after adding many convolution block, the accuracy got till 80, and which is good enough considering the size of the data set. We have only 2000 images, so 80% accuracy is. Oh, anyone has any doubt regarding? Then after the convolution block, we'll flatten all the layers into one array. Like flatten all the flatten the array to like one single 1D array. Then we have a dense like dense layer of 256 channel with railway activation, and we added a 20% dropout up to that. Then then we added a dense layer of 32 channel like railway activation. And this last one is important because we have 6 categories as we see. You can see here you have cardboard, glass, metal, paper. So we need 6 classifications. So we our output channel should be of size 6, channel 6. So here it's 6, and we use softmax activation function as explained in the last channel, last section. And this is basically our model. I'll print the summary of the model. And this is the model. Pooling the key, it divides the matrix by 2. Anyone has any doubt regarding the model? Okay. Now I'll optimize the model and add the loss functions. As the machine learning, like basic machine learning, there is we calculate losses like mean square loss, root mean square, mean like these laws are cross entropy categorical as we did on neural network class session. We used RDAMs. We used both the layer like different kind of. I'll show you one. Give me a second. Just okay. I think it's not. It's, just give me a minute. I'll show that. I'll explain the last session. See, we used both. I'll show you how to wait till I run now. I showed you here, if you remember, using comparing with two, like mean square error and gradient and categorical quotient to be add them. So this gave us about like what you can say 40% accuracy, 40 or 50, something like that. But what Adam and cross entropy did, like it gave us near 90% accuracy. So see, you can see. Okay, 1 minute. Interrupt. I'll use the epoch size. I'll put 5 epochs. This is what Adams gives. Adams and cross entropy. Now after let it run, I'll show you how what SGD and accurate mean squared error does. After this, we'll put. So you can see the what in Adams we get an accuracy of 97%. In the last session's model I'm showing. But in the case of if we use mean square error and gradient descent, I'll tell you. I'll show you the result. Give me just a minute. I'll stop the. I'll just restart. I see the accuracy. You can see the difference. Like it's giving too low accuracy. It will improve obviously, but it goes till like 60 or 70, not much more than that. So like, so Adam is kind of advanced.
Always stick to Adam.
Yeah, just
pretty much.
Yeah, it Adams is like it uses both gradient descent and one more like if you go on to mathematically, it kind of highly optimized you can say. Yeah, just always stick to Adams. It's the best time. Well, compiled our model with the optimizer is Adam and losses. This loss will get printed every in each epoch, and what our aim is in a machine learning is to reduce the loss. So we are using as an optimizer as Adams to reduce the cross entropy loss, and we'll like whatever we get our result, we'll print our matrix as accuracy. So here I did an 10 epochs. I previously trained the model, so this obviously won't start as like a like 80% or this accuracy. It will start slowly, like some 20% accuracy, and each epoch it will improve. But since I previously trained the model, so it's showing like this. So don't like if you're training something and it starts from 20, it's fine. Like it will go on improve till 80 or whatever accuracy it saturates. In the first epoch, it started with losses 0.74 and accuracy is 0.83, and this is training accuracy, and the validation accuracy is 0.78. And when you go to the next epoch, and the training loss is 0.46, like 0.40, the training loss reduced, and training accuracy increased. But the validation loss increased and validation accuracy decreased. So it monitored the model checkpoint monitored this and they didn't save the model to the training.py file. and this is due to the result of this checkpoint. It printed this, and it did, and it didn't save the model to the train model.h5. Then in the next epoch, in the third epoch, there's the training loss reduced to point, the increase and training accuracy reduced. But the validation accuracy loss decreased and validation accuracy increased to 0.79. So due to this, the model checkpoint detected this and basically saved the model in the S5 file, except the weights of this epoch in the S5 file. Like this, it will go on, and on 10th epoch, we have a saturated accuracy as 0.81%, I think, which is good enough for a dataset of size 2000 images. Now since we saved our model, we'll use load model from a TensorFlow.keras model. We'll import the load model and we'll load the model as this. How you load the model? I'll show you how. You have this file. Just copy this path and just load model. We'll save the load model as in the model variable. So load model, and in the parenthesis just put the path name with single quote or double quote, whatever you want, and we'll print the summary of this model. Model summary is this only, like whatever we had in this layer, the same architecture, but we have the weights, and we have now the weights to predict the value, and we'll evaluate the model. Using the test generator. Test generator is basically this dataset. Test dot, like using the test image generator, we rescale the test dataset, like validation dataset, and made the target size 300 and batch size 32. Now this model that evaluates what it does, like evaluates the validation accuracy. So it gave loss as 0.85 and accuracy as 0.79. So you can say that the model, whatever we loaded the model, saved the model. It's giving 79% accuracy, which is, I think, good, pretty decent. Now I'll see the accuracy graph. Like we'll plot training and validation. And okay, before this, if anyone any doubt, like understanding the training of the model and loading the model, I'll just speak of. Anyone has anything to say? I'll go on to next one. So here he plotted the accuracy graphs, training versus validation accuracy. And they're almost like, difference between those is almost like, they're almost parallel. Like validation accuracy is kind of fluctuating, but since we're using a checkpoint, it's fine. Like, whenever it's validate, we're saving only the best one. Like we're saving only the peaks, which the accuracy is high. Like here the peaks where the accuracy is high. Like in the say like the end model days, right? We're not saving this low ones where the validation is fluctuating more from training. So it won't be a problem in predicting the data set. That's the advantage of model checkpoint. Like we just store these peaks and ignore these downs in age epochs. And about plotting this graph, how to plot, I think it's not matplotlib subplot. Like what it does, it divides the plot into two parts. It's in first part it prints accuracy graph. PLT does subplot 211. This is the index of the plot. Like if you put one in this thing, it will print in the first position. If you put 2 in the thing, it will print in second position. Like you can assess more about subplots and plotting, like better with code legends and in the matplotlib library. We didn't cover matplotlib much, but I think it won't. It's not necessary. It's just good for like visualizing the data. Like you can see how our training and validation accuracy high in each epoch. So with matplotlib and all. It's not really needed for machine. It's just for data visualization and visualizing point of view of everything. Now we'll test a prediction. From so we have this prediction file. How is that? We just put off on this file first from this. Okay, like we just I'll give just a second. So cardboard 343, we just copied the path of this and just pasted it here. So we assigned image path as this, and using TensorFlow load image, we loaded the like that image we converted to the 300 plus 300 since everything we used here is 300 plus 300 as input and output. So we feeded the image having 300 and 300 size to TensorFlow, and then we converted the image to array as it will, the model will take array only, no, like as image generator. So and we rescale the image also, and wait, this is basically the title of the loaders image, and IMSO is basically shows the image. You can show without squeeze, I think also. Yeah. Basically, we loaded the image to 300 plus size and converted it into an numpy array, and then rescaled by 255 to what we since we did same as train and test generative, and we kept the title of the plot as loaded image, and we don't need access obviously, and using the imso command we showed the image, and the next is the probability is like P is what it gives is like the confidence of the model, like how much confident the prediction is. Like I haven't printed here, like I can print, I think. I can just print. Wait, give me that. Just put this up. It's giving too much testing. So basically, we loaded the image, and this gives the confidence of the prediction of this. I'll print the P also to show you. P is this array. So what is just key, like how will you predict like the P, like the probability of the like whatever class belongs to it using this array? So we take the first element of this array, and what is just key, like this gives this command, like using the first element of the array, gives the value of the like what 0 1 0 to 6 till we have 0 to 5, no, till labels, the list of labels. So when it gives that, so this labels has this dictionary. I'll show you the labels dictionary. Labels is this cardboard, glass, metal, and paper and plastic and trash. So np.argmax.pe, and that gives value from 0 to like 6. So what it does ki, since if I give that indices to the labels, it will predict the class as like what labels at 0, labels index 0, or labels index 1, or labels index 2, and so whatever we got result from the training, and it will print the image like that. Like here it's predicting the this np.argmax p0 as 0. So since it's predicting that labels and index is 0, so it will print cardboard like that. So, and the confidence is 100 into basically the first element of the arm. I think anyone has any doubt? I'll give it just a little break, then 1 minute, then I'll go to creating set of images. Just give me a minute. So we'll go to the next one. Here we predicted on a single image, as you can see this cardboard, and it gives our model classifies it as a cardboard and at confidence 99.99%. The next set will go to the entire prediction data set. So we'll loop through the entire data set and predict each of the images. I think we imported it here also, so I don't think we, okay, I just imported it again here, so it's fine. So we loaded the model, and our path of prediction is dataset prediction, and don't know why I kept I here. I don't think I is needed here. So we created an empty image list, initiated an image list. We'll store our images. Once we go through the loop, whatever we get, we'll store our images in this image list, and p list is for each image. Whatever the value of p we get, we'll keep it here in the p list. So now in the for loop, so os.listed, what does this does? Like list all the images in the like all the images in the like this only. You can see. Yeah, where is it? Yeah, this. You can list all those images in the using os.listed. So what os.listed is like basically all the images list in the prediction, all these images, and make a list. So for every image path in this, we'll first load the images using target size of 300 and 300. Like since your model is working on 300 plus 300, then we'll convert the image to array, numpy array. Then we'll scale the images, and we'll use our model to predict the p-value of this image. And since we got the array path of image, we'll store the image array to the image list, img list, and all the p values of the respective image in p list. And we get what we get is 43 images in this album. A total 43 images to predict. We'll predict now. So we make a plot of figure size 25 plus 25. And we'll look through each image. So for I in lane of m list is 43, so basically it will loop 43 times for each image, and we'll subplot. Since we have 43, this is what is like number of subplots. Like since it's 9 5, so the subplot will be 9 plus 5, like 5 columns and 9 rows. So rows and columns basically. And this is basically index of that specific like image in the subplot. Like if it's 1, it will stay here. If it's 2, it will stay here. So for each loop, will since first I takes 0, so first image will be 1, so it will stay here. Then the second image will stay here. Then like that. And I don't need squeezing also. I did that. Yeah. So since for each I will predict that specific index from image list, I'll print image list. So big, fine. Like image list is like this. Okay. So if you take the first element of this, basically this array, until this here, this is the first element of the image list. So I'm just removing it because it is becoming too long. And so it gives the first element of the image list as first image, and the same the image list, the respective p value would be p of I. Like the like if image of I is the respective image list of I, like then pi would be the same respective corresponding p value. So now we'll plot the like make the title of the, we want title to be prediction and confidence, right? So we give prediction first, then a space for the whatever prediction value we have. Then we create a new line. Then give some space, and we print confidence after this. Right. Then using the for dot format. Uh, okay. Uh, dot. I think is this covered in the session? The
Which
dot.
one? Format of.
Yeah.
Not really. But it's okay. It's pretty much taking the input you give and placing
Yeah.
it wherever. Yeah.
Like here your first input is this. So basically the first space is this. So what format does ki like the first format list whatever it gets it will store here,
Hmm.
and the second element in the list 100 this element after the comma it will store in the second space.
Instead of
That's
doing format of, you could also just typecast it into strings and add them off.
yeah you can
That's the
also do
same thing.
yeah, and we don't need access obviously, and this is just designing the graphs basically. You can learn it on your own internet. Just tight layout and supply. We give spaces one in each. Like you can just reduce, just don't give 0.1. We'll see how it look like. So this is looking messy, no? If you give 0.1, so just keep it 1 to like make it separate. And we'll show the graph plot. And so this is our prediction. The first one is glass, and it's very low confidence. You can see it's not a glass, so wrong prediction. Obviously there will be some wrong predictions. And the second one is, as you can see in the image, it's cardboard and it's predicted correctly with 100% confidence. The next one is glass. If you did with 87% confidence, and the next one is plastic with 90% confidence, and this one is predicted glass. Like you can see, most of them working fine. Like bearing some of wrong prediction, which is fine, I think.
What I
Since
have done in my offline implementation is, if the prediction is lesser than some percentage, I have classified it as mixed. You could also do that. Like in case the
okay,
program is unsure, it could
yeah,
just
that also so yeah,
yeah.
yeah, actually, yeah. Like you can program it like that so that if the prediction is okay,
Yeah. But like you can do
yeah,
that.
I don't have, I
Hmm.
think. I think most of the prediction are 80, like more than 90% here, 80 or 90, so it's fine prediction. So I'll see what is the result of this. Like, why is giving low confidence? Like in training, well, sometime like there is the law when the validation loss is more, but still the loss is error is more, still the accuracy is high, like testing accuracy. So like this is the result of that. Like, if the error or loss during training or validation is high and the accuracy is as well high, right? So like it's predicting, but with more error, so like less confidence, you can say. And cross entropy loss, like cross entropy is, I can say, a measure of surprise, and like entropy, it's confusing also because entropy is also confusing. But you can like interpret in a like that way. So it's predicting, but it's predicting with less. It's predicting with more loss, like high loss, because it's not confident about its prediction. And that's, you can interpret in the coding result as high loss and high accuracy. That gives them. I think anyone has any doubt in this till now? This will show the tasks then.
Yeah, okay.
I'll stop this.
So before okay, wait, let me share first. Before going into tasks, there are a few things. So we have coded our CNN so far, and we've been running it on our laptops, I think. So before calling it done, we'll have to think about a few more things. So in the end, we are to deploy this onto our waste segregator or whatever project you're doing. Pretty much our case study is in the end to tell you how exactly you design something to solve a social problem. And then we went into mechanical, we went into electronics, we went into software, everything. So yeah, in the end, we have to deploy this program. And when we deploy it, we might get a few limitations. Like, for example, your processor might not have 2 GB RAM or 2 GB VRAM, and you can't exactly load that much data. Then you might have to decrease your batch size in your whatever, like that. So I mean, there'll be some tweaks that you will have to do in order to deploy it successfully. So that is our final step in this software module. So there are a few things you can do. You can tune your model. You can decrease your model size, maybe, like in order to fit it. You could probably decrease your image resolution to improve speed, or you could even add some artificial time delay in your microcontroller so that everything is in sync, maybe. So yeah, that's the thing. So once you are done with design, and then you probably reworked your design, and then you started implementing. You probably reworked it after implementing too. So this is the final step. You Before you deploy it, you tweak it so that it's deployable. And so this is where our summer school ends. I hope our case study of this automatic waste segregator gave a good idea of how exactly we go through designing and implementing. And we have tasks for this session. So this will be the last set of tasks. I will let you guys know about the submission for all three tasks in a bit. I will have to talk to our entire club team and our course before I tell you guys. So here's the task for this session. So there is this data set called MNIST handwritten digits. So this is just grayscale images that comes along with TensorFlow. This is almost like Hello World for CNNs. So what we want you to do is use this code below and import this data set, and then train a CNN to if you give it a handwritten image of size 28 x 28, we want your model to predict it correctly. With aim for an accuracy 80% for starters. It is possible to go till 99%. Like me and AM went till 99.2 ish. So yeah, this is your task for this session. And oh yeah, we also have another meme for this session, and you can find the Google Collaboratory here. I will update the link there. It's right now it's incomplete. I will update it and send you the final slides for this session. Thank you for joining us on this summer school. We hope you had a great time here learning. And yeah, that's it. Thank you.
Thank you.
Thank you for attending.